Up to now, the only specific types of motion that we've considered are constant velocity and constant acceleration. In this mini lesson, we will examine a third type called uniform circular motion. An object moving in a circular path at constant speed is said to be undergoing uniform circular motion. For such an object, its motion is completely characterized by its constant speed v, the radius r of its circular path, and the sense of its rotation, that is, clockwise or counterclockwise. Since a velocity vector always points in the direction of motion, the velocity vector of an object in uniform circular motion is always tangent to its circular path. Even though the speed of the object doesn't change, its direction of motion does change. This means that velocity is constantly changing as the object goes around the circle, because velocity incorporates both magnitude and direction. But since the velocity is changing, the acceleration, which measures the rate of change of velocity, is non-zero. What is the acceleration of an object in uniform circular motion? Let's first consider its direction. If it had a component parallel to the velocity, that would mean the object was either speeding up or slowing down. But it's not. Its speed is constant. And therefore, its acceleration cannot have a component parallel to the velocity. In other words, the acceleration vector of an object in uniform circular motion is always perpendicular to the velocity vector. And since the velocity vector is tangent to the circle, the acceleration vector, which we now know is perpendicular to velocity, lies along a radial line always pointing toward the center of the circle. Why radially inward instead of radially outward? Well, because the direction of motion is always bending toward the center rather than away from it. Incidentally, for this reason, the acceleration for uniform circular motion is called a center-seeking acceleration. The Latin-based word meaning center-seeking is centripetal, and you'll often hear the term centripetal acceleration in reference to circular motion. However, in our experience, this term causes a lot of confusion among students. So we set it aside and instead adopt the term radial acceleration, since the acceleration vector points in the radial direction. The magnitude of the acceleration can only depend on the speed and radius, and it turns out to be v squared over r. I will derive this expression for you at the very end of the mini lesson, but I don't want to take the time to do that now. Putting everything together, we see that the acceleration vector for an object in uniform circular motion is a equals v squared over r, pointing radially inward. Notice that for a given speed and radius, the magnitude of the acceleration is constant. However, its direction is not constant. It always points radially inward, so its direction changes as the object sweeps out its path. So this is not a constant acceleration situation, even though the magnitude of a is unchanging. A word of caution: do not make the mistake of using constant acceleration equations for uniform circular motion. They simply do not apply here. Okay, let's do an example. Angela's mountain bike is inverted on the ground as she fixes the chain. To test the repair, she turns the pedal so that the front wheel rotates at constant speed. Suddenly, a small pebble that had been lodged in the tread becomes free right when its radial line with the axle is at an angle of 60 degrees with respect to horizontal. The pebble sails through the air and lands on the ground, having gone a horizontal distance of 235 centimeters. The radius of the bicycle tire is 33 centimeters, and the height of the axle above the ground is 41 centimeters. What was the magnitude of the pebble's acceleration before it became dislodged from the tire tread? The problem provides us with a picture, so we don't need to do the usual drawing step. However, we ought to think about the problem and reason through our strategy for solving it before jumping in and writing down equations. We're asked to determine the acceleration of the pebble before it became dislodged from the tire tread. Since the tire, we're told, rotates at constant speed, the lodged pebble is undergoing uniform circular motion about the wheel axle. That means its acceleration is v squared over r. We're given r, but we don't know v. So our job now is to find v. The instant the pebble dislodges from the tire tread, it's no longer in uniform circular motion. Why? Because nothing is keeping it going in a circular path anymore. In fact, the only thing affecting its motion now is gravity, and that means it's in free fall. The pebble's velocity the instant after it dislodges from the tire is the same as its velocity the instant before dislodging. So if we can compute the initial velocity of the free fall part, that will also be its velocity the moment before it dislodges from the tire while it's still in uniform circular motion. The magnitude of that velocity will be the speed v we're looking for. By now, we know how to approach free fall problems. We first parse the problem into initial and final events. For this problem, they are the pebble dislodging from the tire and the pebble landing on the ground, respectively. Next, we organize our knowledge of the kinematic variables for both events. To do that, though, we first need to augment the figure a bit. We are not directly given the initial height of the pebble, but we are given enough information to figure it out. The height of the pebble above the axle, just as it dislodges, is 33 centimeters times sine of 60 degrees. And the height of the axle above the ground level is 41 centimeters. So the initial height of the pebble above the ground is 41 centimeters plus 33 centimeters times sine 60 degrees, which equals 69.6 centimeters, or 0.696 meters. It's usually necessary to use a consistent set of units throughout the problem, and since we usually express g in terms of meters per second squared, we might as well convert all lengths from centimeters to meters. The initial velocity vector for the free fall part of the motion is tangent to the wheel at the point where it became dislodged. A little bit of angle geometry tells us that the initial velocity vector, v0, makes a 60-degree angle with the vertical. Now we're ready to tabulate the kinematic variables. We choose the zero of time to be at the initial event and the origin of coordinates to be at ground level just below the initial position of the pebble. With these choices, t0, x0, and y final are all 0. X final equals 2.35 meters, which were given in the problem, and y0 equals 0.696 meters, as we just previously computed. We don't know the initial speed v. That's what we're looking to calculate after all. But we do know the initial direction of motion. So we can express the components of the initial velocity vector in terms of a single unknown v. In particular, the x component of the initial velocity is equal to v times sine of 60 degrees, and the y component is equal to v times cosine of 60 degrees. As always, the acceleration of an object in free fall is 9.8 meters per second squared straight down. So a sub x equals 0, and a sub y equals minus g, or minus 9.8 meters per second squared. The unknowns in this problem are the initial speed v, which is what we're looking for after all, the final time t sub f, and the y component of the final velocity v sub fy. Okay, we're now ready to calculate. Let's start with the first constant acceleration equation for the x motion. Plugging in numbers gives 2.35 equals v sine 60 degrees times t final. This equation has two unknowns, so we can't solve for v yet. We need another equation in these two unknowns. We get that from the first constant acceleration equation for the y motion. Plugging in numbers gives 0 equals 0.696 plus v cosine 60 degrees times t final minus 1/2 times 9.8 times t final squared. Now we have two equations in two unknowns, which means we can solve for both. Actually, all we really need is v, so let's eliminate t final. Solving the first equation for t final in terms of v gives t final equals 2.71 divided by v. Now we plug that into the second equation and solve for v to obtain v squared equals 17.6 meters squared per second squared. We can now take the square root to get v, but there's really no need to do that since v squared is what appears in the expression for the radial acceleration. We're now ready to answer the question posed in the problem. What was the magnitude of the pebble's acceleration before it became dislodged from the tire tread? Well, that's just v squared over r, which equals 17.6 meters squared per second squared divided by 0.33 meters, or 53.3 meters per second squared. We're done with the example problem, but earlier I promised that I'd derive the equation a equals v squared over r for the magnitude of the acceleration of uniform circular motion. Let's consider a very brief time interval delta t for an object in uniform circular motion. In that time, the object sweeps out a small angle delta theta. In the figure, I've exaggerated the size of the angle swept out just for the sake of readability. In reality, we should imagine the object sweeping out a very tiny angle in a very tiny time interval. The velocity vector, which remains tangent to the circle, changes by a small vector delta v. Since the speed remains constant, the length of the two velocity vectors v1 and v2 in this figure are the same, namely v. By elementary geometry, the angle between v1 and v2 is the same as the angle swept out by the object, namely delta theta. The acceleration is given by a equals delta v divided by delta t. Let's see how we use this to find a relationship between a, v, and r. If delta theta is truly tiny, which it will be if delta t is tiny, then the magnitude of delta v is just the length of either of the two sides times delta theta, or magnitude of delta v equals v delta theta. The time interval delta t is equal to the distance the object travels, which is just the length of the arc swept out, divided by its speed, v. For a circle, arc length equals the angle swept out times the radius of the circle, or r delta theta. So we find that delta t equals r delta theta divided by v. Putting this all together, the magnitude of the acceleration of an object in uniform circular motion is a, which is just the magnitude of the acceleration vector, equals the magnitude of delta v divided by delta t, which equals v times delta theta times the quantity v over r delta theta. That's equal to, canceling out the delta thetas, v squared over r, which is what we set out to derive. One small note for those of you who worry about details. In order for the magnitude of delta v to be equal to v delta theta, and the arc length to be r delta theta, in order for that to be true, the angle delta theta technically must be in radians, not degrees. And if you don't know what radians are, I leave it to you to look it up on, say, Wikipedia. But degrees and radians are proportional to each other. So since in the end I'm taking a ratio and the delta thetas drop out, it actually doesn't really matter which angle units I use. I still get the result that A equals v squared over r.